Hey everybody, it's Dr. J, and today, we're talking about periodic trends. Let's talk chemistry. All right, so the first trend we're going to talk about is atomic radius. Atomic radius is basically a set of average bonding radii determined from measurements on a large number of elements and compounds. All right. So basically, when we're thinking about atomic radius, it's going to represent the radius of an atom when it's bonded to another atom. So I got two different examples here. Basically, we got a van der Waals radius, and then we got covalent radius. The key thing you want to understand, van der Waals radius is basically one half of the distance between the adjacent nuclei in an atomic solid. So if we think about, in this case, krypton, this is a solid here. We understand with a solid, we got all of our atoms close together, right? So they're not like gases or liquids. And because they're right by each other, we can find the atomic radius. And basically, essentially, when we're looking at atomic radius, we're just taking it from the middle to the middle there. Okay, that's it. All right, so the middle of the atom to the other middle of the next atom. Okay. And real quickly, we're going to talk about bromine. The covalent radius is one half of the distance between two bonded atoms. Basically, guys, it's the same thing. We're looking at the middle of the atom to the other middle of the next atom. All right, so just depending on how they're bound, it's going to impact, the distance between those atoms, right? And covalent, or if you, in this case, you just got some van der Waals. So basically, right here, we're going to do find our bromine radius. We'll take the middle and middle. Now we have our length, and then we're just going to divide it by 2 in this case. We get 114 for our atomic radius. So let's talk about the trends though with atomic radius, right? So if you look at the periodic table, you can actually tell a lot. And one of those trends is atomic radius. Now, the atomic radius trend is actually determined by the valence electrons. So we look over here, right? We got our different atomic radius for each elements. In this case, I got a couple over here. One trend to pay attention to is the columns. So remember, those are the family groups, alkaline metals, alkaline earth metals, halogens, all those type of family groups. So if you pay attention to just the column, the atomic radius will actually increase if you go down the column. Now, the reason why it's increasing as we go down the column is because, right, what's happening? What's happening, right? They're getting bigger. They're getting bigger as we go down a column. And basically, if our elements are getting bigger, that means that we're going to have more electrons. And therefore, we got more electrons. That means that we're going to have more shells to fill up, right? So that's going to impact our atomic radius just because we got more electrons. The same thing will be applied if we go across our periodic table. So if we're going towards the right of our periodic table, basically our atomic radius will decrease. Now, the reason being is because we have something that's called effective nuclear charge. That's one of the trends we will talk about in this video. So please stay tuned at the very end of the video where we're going to be talking about effective nuclear charge. But basically, this deals with the attraction between those two. So basically, because of this attraction, it's going to become greater as we add protons to the nucleus. Now, we all know as we go across the periodic table, we're always going to be adding protons. And now we're going to have this bigger attraction. Therefore, it's going to be impacting my atomic radius. So basically, if we go towards the right, we're decreasing right in our atomic radius. And we can see that right if we go towards the very right from lithium all the way to neon, our atomic radius has decreased. And if we go from lithium down or beryllium down to barium, right? If we look at another row, we just go down this column, we can see what's happening is increasing, right? So we can look at these different trends here. And this is a nice little chart I like to show. If you look here, right, guess what we see? We're going to see all of our alkali metals. And if we compare those to just our noble gases, right, we can see that our alkali metals are what? They have a larger radius, right? Because they're on the most left side of our periodic table. And then if we look towards our right, then our right has our noble gases. And because they're on the furthest right, in this case, what do we notice about the atomic radius? It's very, very small. So we talked about atomic radius, but there's also ionic radius. All right, so these are very similar. The key thing we want to focus on, right, is we're still talking about the radius of our atom or element in this case. But now instead of focusing on the atom, now we're looking at the ion. Okay. So cations are usually going to be smaller than your neutral atoms. Anions are usually larger than your neutral atoms. So basically, we understand this trend. You guys are going to be good with ionic radius. Larger positive charge equals a smaller cation. And a larger negative charge means that you got a larger anion. So basically, if we go to group 1A, right, those alkali metals, if we compare, right, going from the regular atom to the lithium cation, right, we can see that the radius was going to be dramatically different. In this case, it's very, very smaller than your normal atom, as we can see with this lithium cation. Okay. And then if we go on the anion side and we look at fluorine, right? Fluorine is normally 72, but once it gains that electron, okay, now the radius is bigger, right? So this all makes sense, right? Anions are gaining electrons. Because they're gaining electrons, the radius is going to change. Cations are losing electrons, so because they're losing electrons, the radius will change. So here's the next trend, the effective nuclear charge. So what we mentioned earlier, now let's talk about it. So basically in multi-electron type of atoms, electrons are going to be attracted to your nucleus, okay? And then they're also going to be repelled by each other. So a lot of stuff is going on, right? So those outer electrons, as we mentioned before, are going to be shielded from the nucleus by the core electrons, and electrons in the same shell don't shield each other from the nucleus. Okay. So because of this, a couple of different things will happen. It's going to basically decrease your atomic radius as we across the row. So that's what we were talking about before, right? Because of this different charges, this is going to impact our atomic radius now, as well as the elements as they add a proton, right? That means that we're going to be increasing attraction to the nucleus. So that's the reason why we saw the attraction increase in this case, impacting our radius as we went towards the right, because we're always adding a proton if we're going towards the right. And as well as if you're adding a proton, you're probably adding another electron, and there's no shielding in the same shell. Okay. So the technical definition of effective nuclear charge, or ZF, if you see this symbol over here, is a net positive charge that is attracting a particular electron. Once again, a net positive charge that is attracting a particular electron. So in this case, if we look down here to the effective nuclear charge equation, right, we're just going to look at the equation and go from there. Z is our nuclear charge. And then S is going to be the number of electrons in the lower energy levels. So, as we mentioned before, in this case, when we're talking about effective nuclear charge, if we move to the right, across, that row in our periodic table. So as we go towards the right, the effective nuclear charge that is experienced by the electrons in the outermost shell, right, will increase. Okay, so it's going to be increasing as we go towards the right for effective nuclear charge. So because of this increase, as we mentioned before, of all the different reasons, means that it's going to have a stronger attraction between our outermost electrons and the nucleus, right? And if you got a stronger attraction, then you're also going to have a small atomic radius in, okay? And if we look at this quick example, say we got a +3 in our nucleus for the charge, we got our core electrons in our 1s2 orbital shell, and then we got our one valence electron in the outermost shell here, okay? So we got our 1s2, we got our valence, 2s1, and when we go to do our actual effective nuclear charge, we can see that in this case, our Z, the nuclear charge, is +3, and our S, the number of electrons in the lower energy levels, so those are our core electrons basically, is 2. So 3 minus 2 is going to give me an effective nuclear charge of +1 here. Okay. So this is our effective nuclear charge.